WGPU-PY is a Python implementation of WebGPU, and PyGFX is a Python rendering engine for WebGPU based on WGPU-PY. This rendering engine enables the creation of a wide variety of graphics applications in Python. Its high-level abstractions make it easy to begin coding with WebGPU, while also allowing developers to craft custom and optimized rendering solutions. With just a few lines of code, intricate 3D objects can be created, as demonstrated on your screen. Hello everyone. Welcome to my YouTube channel, Practical Programming with Dr. Sue. Before delving into coding, let's briefly review the development of graphics APIs. While OpenGL has been popular for decades, it was not designed for modern hardware and software architectures. As more powerful hardware emerged, OpenGL revealed limitations in performance and functionality. This led to the development of new graphics APIs such as Vulkan, Metal, and DirectX 12, designed to fully leverage modern hardware and software architectures. However, these APIs are very low-level, requiring over 1,000 lines of code even for rendering a simple triangle. Despite the availability of these new graphics APIs, there remains a need for a unified API suitable for both native devices and the web. This is where WebGPU comes into play. WebGPU is tailored for the web and implemented on top of Vulkan, Metal, and DirectX 12. It stands out as the only truly cross-platform, modern graphics API for web applications. WGPU-PY serves as a simple Python implementation for WebGPU. Both WebGPU and WGPU-PY are higher level compared to Vulkan, Metal, and DirectX 12, though still relatively low level. For a triangle example, they require about 100 lines of code. To further simplify coding, a much higher-level render engine named PyGFX is proposed. This render engine can be used to create a wide variety of graphics applications in Python. Its high-level abstractions make it easy to start coding with WebGPU, while also enabling developers to create custom and optimized rendering solutions. For a triangle example, it only requires fewer than 20 lines of code. In this video series, we'll use the PyGFX render engine to create a variety of stunning 3D graphics. Today, I will showcase the capabilities of this rendering engine by generating 3D objects with different materials that seamlessly interact with the environment. This demonstration aims to illustrate how easily complex objects can be constructed in Python using this engine. I assume you possess a basic understanding of Python programming. However, if you're unfamiliar with WebGPU and the PyGFX rendering engine, I'll guide you through each step of the process, including transformation and shader code. If you want to follow along with this video, you'll first need to create a virtual environment and then install the PyGFX package within the virtual environment using the following command. Here, glfw serves as a lightweight window for rendering. We are currently using version 0.1.17 of the PyGFX rendering engine. If you install other versions, you may be able to run most examples with few modifications, but please be aware that this video series is intended for the specified version on which all example programs were created and tested. It is recommended to run the same code on the same engine version. Additionally, ensure that you have a modern graphics card and pip version 20.3 or later. In this video series, we'll organize our Python code with the following structure. First is the root directory containing 3 folders: Assets, Common, and SRC. The Assets folder consists of static files such as images, fonts, and model files. The Common folder contains commonly used files that can be reused in multiple examples, such as helper and utility functions. The main folder is SRC that stores all source code used in implementing example projects. This folder further includes many subfolders, such as Video 01, Video 02, etc., with each subfolder containing source code used for creating the examples presented in that specific video. You can run example projects from the root directory. For instance, if we run a project implemented in the test.py file located in the src/video01 folder, we can execute it with the following command. Before delving into the detailed programming steps, let's begin with a simple example demonstrating how to utilize the PyGFX rendering engine. Initially, we import the PyGFX rendering engine and proceed to create a torus knot object. The torus knot geometry function is employed to generate the geometry for a torus knot based on a set of parameters. Simultaneously, the mesh fong material function is used to create a fong material for the mesh, giving it a red color. The ifname main block guarantees that the enclosed code is executed only when the script is run directly. The gfxShow function is then utilized to display the 3D mesh in a glfw window. The gfxShow function is a utility function that has many optional input arguments, including canvas, renderer, controller, camera, etc. Here is a detailed explanation of these arguments. In our current simple example, we simply use the default input parameters. This simple code script effectively renders our first 3D torus knot object. It is worth noting that the color in the PyGFX engine can be easily specified in various ways, including color names, hex numbers, and floating point values. Similar to modern browsers, the PyGFX engine supports 140 named colors. Below is a list of these color names along with their corresponding hex and RGB codes. Most colors in PyGFX are defined using floating point values that typically consist of 4 components. However, it is also possible to specify colors with 1 to 4 components. A single scalar value corresponds to a grayscale intensity, like this. Its RGB components have the same value specified by this scalar value. 2 values correspond to a grayscale intensity along with an alpha channel. 3 values correspond to the red, green, and blue components. 4 components collectively represent RGB and the alpha channel. Now, let's explore a different approach to changing the object's color. First, let's modify the color name to gold. This adjustment will render the torus knot in a gold hue. This method allows you to choose any named color you prefer. Furthermore, we have the option to use a single scalar number to denote a grayscale color. If we set the color to 0, the object will appear in black. Conversely, if we set it to 1, we will observe a white torus knot. Additionally, we can use 2 numbers to represent grayscale intensity along with an alpha channel. For instance, setting the color to 0, 0.5 will result in a partially transparent black object. More commonly, we use 3 numbers to specify an RGB color. For instance, setting the color to 1, 1, 0 will result in a yellow torus knot. Next, we'll demonstrate how to add a skybox to the scene using environment cube mapping. You might notice that game engines and sophisticated 3D scenes often use skyboxes because they play a crucial role in enhancing the visual quality, realism, and immersion of 3D environments. They contribute to the overall aesthetics of 3D scenes and provide a practical solution for creating expansive virtual worlds. Here, we'll place our torus knot objects, which we just created previously, into Skybox environments and showcase how the amazing visual effects can be added to the 3D objects. Now, let's start implementing the Skybox using cube mapping. For reuse purposes, we'll create a separate Python file named helper.py in the common directory. In this file, we first need to import necessary modules, including the PyGFX rendering engine and the ImageIO module for loading image data. We then define a Python function called createCubeMap. Subsequently, we load a CubeMap image from the ImageIO library. Of course, you can use your own CubeMap images or download them from internet. The cube map is then processed to fit the required shape, and 2 texture objects, env static and env dynamic, are created to represent environment maps. The function finally returns these 2 environment maps. If you're unable to fully understand the code, that's okay. We'll explain it in more detail later. Next, we will use this cube map as a Skybox environment to create our torus knot object. First, we need to import necessary modules, including the PyGFX rendering engine and the cube camera for view the Skybox, as well as our helper function created previously in the common folder. Subsequently, we create a scene and generate the static and dynamic Skybox environments by calling the createCubeMap function from the helper module. We then create a cube camera and set up the background with a Skybox using the code below. Here, the camera will be used to render the scene from different cube map faces, and the background is created with a background Skybox material using the env static texture. Next, we create a torus knot object with a specific material using the following code. Here, the mesh standard material is generated with specific properties like roughness and metalness. The material is assigned the env dynamic texture as an environment map. A torus knot is then created using the torus knot geometry function and the previously defined material. Finally, we render the scene using the cube camera and display it using the GFX show function with the following code. This code generates a visually appealing torus knot object that interacts with the surrounding environment. In PyGFX, performing animations is a straightforward process. If we want an object to rotate continuously, animation provides a solution. First, import the Python linear algebra utility module, and then define a function named animate. Inside this function, create a rotation from a quaternion based on Euler angles and assign it to the object's rotation property. We also perform a similar animation for our Skybox background. Finally, set the displays before render attribute to this animate function. The before render property is a callback executed during each draw call before a new render is made. Running this code generates a torus knot object with continuous rotation. Additionally, in PyGFX, modifying the object's appearance is easily achieved by adjusting material properties. Here, we set the material's envMap attribute to envDynamic. Changing this attribute to envStatic yields a different-looking torus knot, as displayed on the screen. Environment mapping is a computationally efficient method of creating the illusion of reflections and refractions. The concept involves using a texture arranged like a cube to represent the world for an object to reflect. The key distinction between dynamic and static environments is that envStatic is a pre-made texture, while envDynamic is a rendering of the scene around the object. Furthermore, a glass-like object can be created by specifying the material's env mapping mode property using the cube refraction. In PyGFX, generating various built-in shapes is simple by substituting the geometry. For example, a box object can be created using the box geometry. This creates a glass-like cube as demonstrated on the screen. This is just an introduction to this video series about WebGPU in Python. It showcases how easy it is to create stunning 3D objects in the PyGFX rendering engine. In the following videos, we'll delve into the programming details.